hope everyone's doing well and stuff from lunch today. So today I'll be talking to you guys about characterization of quantum cascade lasers on silicon. My major is in electrical engineering. And here at this AIM internship, I was significantly lucky enough to have two mentors, Alexander Spott and Robert Zhang. And also, I was fortunate enough to be working under the faculty advisor, John Bowers. The quantum cascade lasers emit light in the mid-infrared wavelengths. We are interested in these mid-infrared wavelengths because it has approximately 2 to 20 microns. Another benefit with these mid-infrared wavelengths is that it benefits us with many different applications with varieties of sensors and detectors. Here we have 4 different applications, from chemical bond spectroscopy, gas sensing, biological sensing, and remote sensing. Here we have a picture of a quantum cascade laser on top of a silicon platform. We want to use the mid-infrared lasers on the silicon because of the many advantages that silicon offers. Mid-infrared silicon photonic integration offers us inexpensive, compact devices with a large optical bandwidth. Not only that, but silicon also offers us, with these silicon waveguides, a low optical loss. So mid-infrared silicon photonic integration is very beneficial to us, and we can have multiple applications on one chip. Throughout my research here, I was trying to get an understanding of these quantum cascade lasers on silicon. I was taking measurements of different lasers that have a different internal geometry. And another thing is that what I wanted to understand with these quantum cascade lasers is the internal geometry and match that with theoretical data from the laser theory. Another thing is what the internal geometries varies from laser to laser, and my mentor wants to build the next generation of chips, so we would want to understand what is going on inside these internal geometries of the laser. Here you see a picture of the same laser from the previous page and a cross-section laser of the cross-section of the laser active region. So the internal geometry that I'm talking about varies from the 3.5 Mesa width and the silicon waveguide width. Here on top you see is our 3.5 Mesa width. It varies from 4 to 8 microns. And at the bottom we have our silicon waveguide width that varies from 1.5 microns to 3.5 microns. Throughout the research, the question is, what I'm trying to answer is, which one of these internal geometries perform better? So before I'm able to take data from any of these lasers, I first have to have my lab set up. Here we have our chip that is mounted on top of a temperature control stage. This temperature control stage is set at 20 degrees Celsius. We set it here because we want to understand these lasers. We want to understand these lasers in room temperature and get an understanding with these internal geometry. Before I'm able to get any energy from the photon emitted from the laser, I first have to send current. We send current pulses through the wires into the probes, and at the end of the probes we have these needle probes contacting the top pads of the lasers. Once we have sent current through these probes, the photodetector then detects the photons emitted from the laser. Here is a close-up picture of a chip. There is actually 35 lasers on this single chip. The lasers are actually horizontal, and these needle probes are contacting the top pads of one laser bridge. Here we have 3 different internal geometries that we want to, what I'm trying to understand. These are just pointing to 3 of them because every single one of these lasers has a different internal geometry in which we would want to get a better understanding of. These needle probes is where the current gets sent to. These needle probes are contacting the top probe pad and the bottom probe pad. The needle probes vary throughout the laser, so we can send current equally on the laser. Here you see is the top picture of one laser and the cross-section of the laser. So when current gets sent through, it gets sent through the top probe pad. It goes through this metal down to the active region, and it ends up back to the bottom probe pad. So when I be analyzing these lasers and getting data from them, I first was able to get these LI graphs. These LI graphs is the light output versus our current, which you have here on the Y and the X axis. At the bottom, you see the picture of the different internal geometries. We only have two different devices because there are different devices on these lasers. Here is a threshold current. This threshold current tells us where this laser has been activated. This threshold current here has a 307 milliamp, and the threshold current over here has a 354 milliamp. The lower the threshold current, the better, because that tells us that we just have to send current. We have to send less current than throughout the other lasers. Here are several different devices that I have been tested, that I have gotten data from that I tested. Here you see our silicon waveguide width. It varies from 0.5 to 2.5, and there's more. Also, we have our threshold current over here on the left. These green and blue tells us the mesa width, the 3.5 mesa width. As of right now, we have only gotten data from several of these devices. We are little by little we're trying to see we are seeing a trend, but we can't make an assumption of what is actually going on with these internal geometries. So throughout this research, what I've been doing is trying to get more data so we can figure out what is affecting these internal geometries, so we can get a better understanding of them. So in conclusion, so far I have gotten data from just one single chip, and we would like to further our experiments to get more data from different chips so we can get an understanding of these internal geometries. We want to build new lasers with optimal internal geometry. And that's what I've been helping out with my mentor. I've been trying to get data from these lasers so that he can build the next generations of chips. I would like to acknowledge my mentors Alexander Spa and Robert Zane for helping me throughout my internship here. They have been very helpful, and don't mind me asking many questions and calling them or emailing them at night. Also, I would like to thank faculty Professor John Bowers for giving me an opportunity to be able to work with these great mentors here, and an opportunity to be working in his lab. It's such an amazing lab, and not only that, but also the graduate students in these labs are amazing. They help me out when I needed help, and many things that they have done when I'm stuck in lab. I would also like to thank the AIM Photonics Internship Program and coordinator Wendy Ibsen, Jens, Stephanie, and Maria, who is in here. Thank you.